But welcome to Unplugged Unmuted. I'm your host, Ryan. If you'd like to introduce yourself, your profession, what you do, it'd be perfect.
Okay. Well, I'm Henry Duwe. I am an assistant professor at Iowa State here. I'm in the electrical and computer engineering department. My focus area is computer architecture. So I view that as building computer chips or designing computer chips, and I sit at the interface between software and hardware.
What got you into that? If was there like a certain point in your life where you're like, this is the bee's knees, you know what I mean?
So that's a longer story.
That's fine.
So yeah, at some point there was a moment, probably when I was an undergraduate, where I was like, yeah, I want to know how to design a chip. I want to design chips. So I guess the longer story to get there was that I guess I've always been curious, and I maybe was 5 when my father had brought home a laptop, and this is early '90s laptop, an Apple laptop at the time, and had some games on it that I didn't know the rules of the games. I didn't know how to play them. My dad didn't care to play games, so I was figuring it out without knowing how to read, at that point or anything, and just playing games. And so apparently Apple didn't have a lot of games on it at the time. It was not that was not their thing. Education was kind of their niche market that they were in at the time. This was kind of in some of their darker years. They weren't the popular computer at the time. And I just want to know, how does it work? Because I was surprised that you could do anything on it. It seemed, and to be honest, I didn't do much with computers. Actually, I actually didn't play very many games. I didn't have an immersive computer, background. So I wasn't really into computers. I was very curious, and so I tended towards science topics. In math, and in high school, I gravitated towards biochemistry, taking AP chemistry, and the types of courses that would set me on a path to do biochemistry work. And as I was a junior, I think in high school, we had an option to do a research project, and we basically tried to find a faculty at our local university. I grew up in Madison, so the University of Wisconsin, and try to do research with them. And so I ended up, gravitating towards bioinformatics and computational biochemistry. So, we were looking at protein folding applications, and so that was my introduction to C programming.
What kind of objectives you're trying to accomplish with C programming with that?
Well, we were modeling the physical forces of the atomic components of a chain of amino acids.
That was your introduction to C.
Yeah, and I got wrapped into helping a sophomore in college, right? So an undergraduate who was ended up being my roommate later on, and was a very smart individual, but so he was doing a lot of the higher level software construction. I was doing some the lower level tasks that needed to be done to fit into point A, point B, but definitely learned a lot about pointers and pointer math, and how painful that was when I was So I was rolling into my senior year then so in high school. So that's that got me interested in taking computer science courses.
So did your high school actually teach C, or is it kind of like a dual program through?
Nope. I was learning from so yeah, there's a couple books. There's the the one that I've always kept, which is K&R book, which kind of has the definitive book on C. It's cool. It has, if you look at the back cover, it has the context-free grammar of C and so forth. So it's fun to have that around. So I was using that and one of, I don't know, some other book. And
So you basically taught yourself C.
yeah, and I had a goal, I had a purpose. So having a purpose is helpful.
That's I'll give you very big props for that, because it's like one of the first classes here for anyone that doesn't go to Iowa State is CprE or SE 185, and in that class you're learning C. It's very bare bones, and at the end of the class, as high as you go is like Malik. So you do your pointers and stuff. Pointers as a freshman incoming is a very difficult subject to go through, and at your time with Iowa State is you go through various C classes. You have 185, you have 288, you have 308. And any other, if you take embedded systems too with Dr. Jones, that class as well. But like C is a very stripped language of a lot of very nice things like higher level languages it has. So that's actually very impressive to me that you taught yourself C.
Yeah, in defense of low level languages, I teach 381, which
Right.
you learn a lot about C whether you like it or not. We don't teach C, but you're supposed to have it, so you learn a lot about it because you're translating it into more basic instructions. But I think C looks a lot like a lot of math that you do. So yes, there's the big difference is you have an address of a location, but you don't have a lot of the I look at a lot of the other higher level languages, domain specific languages that are really extensible. They have so many features that are hard to wrap your head around, right? If you haven't done a fair bit of background work on them. So I actually think C isn't that awful of an introduction.
Yeah, it's not. I think one of the nicest languages to go into. So it's like if you can learn C, you can learn any of the languages. I feel, because to me C is the most difficult, but it's also a nice starting point, as it's one of the most bare bones languages you can start out with. You're not dealing with the thousands of Python libraries out there. You're not dealing with just a lot of stuff where it might be thought of where it's like there's just so much to learn. C is like the main C library itself. Before you import anything or include anything, it's very basic, but you can still do a lot with it, and teaches you a lot about how programming works. Teaches you can debug with it. That's actually something I figured out. This is my senior year. This is my last semester here. I just figured out how. What was it? GDB or GBD?
GDB.
GDB. Yeah, I just learned about that. Like, are you kidding me?
Well, I mean, this is a bit of a tangent, but I was probably a junior when I figured out how to effectively use GDB, right? And we had a design automation course. So basically, we were actually building tools to do back-end chip design. Basically, once you have a circuit, how you're going to do place and route of the standard cells, the wires that wire up between the standard cells, etc. And this, this is you have to build data structures to do this efficiently. And we got a choice. Our CS department was a Java-only shop, so unfortunately I had operating systems in Java. And computer engineering was more C-focused, but this is a computer engineering course, and you could do it in whatever language you wanted. Just here's an input file, go forth and do sort of task. And I found an interesting. I learned a lot from that project. That I spent a lot of time working on. I learned, I was building, complex graph structures in data structures in C, and that's painful and very easy to screw things up. So GDB was essential. So I learned a lot practically about using GDB that semester. I also learned that my C program ran, in 30 seconds to 2 minutes, whereas the students who were doing Java versions and using fancy Java libraries, they were running in 30 plus minutes. And they did have one advantage for debugging: a very fast debug cycle.
Yeah.
So they'd run it for 30 minutes and it would maybe hang or crash or produce a non-usable result. But I'd have, from end to end, it would run a couple of minutes in the worst case, and if it crashed, it would crash very quickly. So I got the result quickly.
Yeah, so that is the actually nice thing about C. It's a very fast compilation and runtime as compared to your higher level languages because it's more stripped down. There's less really to deal with. I'd say C is like as binary is to assembly is to C, and then Python's actually built on top of C. So it's like there's less intermediary steps for actually like compiling and running the code. Is that a fair assumption? I feel like I shouldn't be saying that so confidently.
So, as with all things, it depends, but in general, yeah, right? That you're, Python, depending on what libraries you're using, et cetera, yes, may actually have compiled C backends and may be, relatively efficient, but in the raw form, if you're not really optimizing it, and you don't have that depth of knowledge of how you're going to, what you're using underneath it, it can be hugely inefficient.
Yeah. So I think what you're referring to is just like your big O times and stuff like that, and because because like sure we can compare like something like O squared time. If you have something like log n time, that's a way you're talking about two different types of executions right there. Yeah. Is that what you're referring to?
Well, we're talking probably about the constant in front, right? So big right. O is some it's big O of n is some constant times n.
Right.
Right. So that constant, right, is the issue, right? If I implement an algorithm that's the same algorithm in C and in Python, it's really that constant that changes. So, if it becomes unscalable in complexity, it's still going to be unscalable in C.
Yeah. So I guess continuing with your college career, were there any classes where you're like, was there anything that almost got you to your breaking point at all, or were you just like kind of like a steady, keeping your nose to the grindstone student?
So if I may, I can.
Yeah.
Can we go back to the original question? So why, when did I decide to be a computer engineer?
Yeah.
Right? So I took. I wanted to be a computational biochemist, right?
Yep.
So I ended up taking a lot of, my prereq courses for biochemistry. As a agriculture, College of Agriculture and Life Sciences student, and I was taking computer science courses on the side. Sometimes during the summer, sometimes not. And I think I took digital logic during the summer. I don't know if it was my first summer or my second summer. And took digital logic. I took it from a faculty who didn't probably care about digital logic, and certainly wasn't in the area. But despite kind of the lackluster interaction, I loved the material. I loved the tools and what we were doing, and these were terrible tools. Yeah, students today have much better CAD tools that they.
Yeah, because you probably didn't have Cordis back then, did you?
So we were working in old Mentor graphics flow, and it was on I don't know if it's on Solaris. So we had these were old 3-button mice, and you would have to do a lot of manipulation of graphical manipulation. There was less support for scripting, although it did definitely cause me to get down into scripting and trying to automate testing and stuff. But yeah, that process, that interaction of got me interested in computer engineering. It was scratching the itch of back to that kind of first laptop, like how do these things work? And as part of our the background chemistry and physics courses that I had to take for my biochemistry, and to get around certain requirements, we weren't allowed to skip out of intro chemistry, even though we had very good AP scores. So I took chemical engineering chemistry, which started with Schrodinger's equation, and so it was a physics-based chemistry. And so all of a sudden, I was getting the physics end of kind of how does a transistor work? How can it work? Is it kind of a tangent in one of those classes, and bringing that together with building up circuits on top of it. And I was just wanted to get to know how a computer comes to be. Like, how do you make this useful device? And so that's probably where, whether I really knew it at the time or not, it was like I want to design computer systems. So
Has there even been any projects that you want to talk about in terms of your basic computer chip architecture? Like, have you designed anything for any chip manufacturing company or in your own projects?
So no, I don't have any commercial products. So I have only worked for internship. So I worked for AMD for 8-9 months, and interestingly, I wasn't on the design or even the verification team. I was I worked on a PCB board design team for their margin testing system. And so most of the people I was working with, their electrical engineering background. And my role was to write FPGA system Verilog firmware that would do two things. One, basically just manage the boards, manage parts of the bring up and testing interfaces. Okay, so it was not it was external to the chip design, and then just actually write code that would test that code. So again, it was this is code that was written by effectively non-computer engineers to kind of at the time get the job done, and they wanted it transformed into have automated tests and get it to be at least more robust to changes, and to be able to be confident that part of the testing board was tested. So had a lot of freedom, and it was a really good experience. But the reason I think it was a good experience is because I was learning very different things, very practical things about chip manufacturing, and because you have to test things, right? You have to test the chips after they are fabricated, and so this is just something that is often, is covered in courses, but you don't appreciate the time, effort, and thought that it really, really takes to manufacture and test and bring up chips. So that has stuck with me, that experience, quite a bit. But no, I don't have a chip out there.
No, I didn't expect like you single-handedly to. I didn't know if you like contributed to a team that put a product out in the market.
No.
But no, that's fine. I'm not. You got your entire career ahead. If that's something you want to do, well, I guess looking at your career, I guess why did you want to be a professor?
It's sometimes it wasn't. It's not clear initially, right? It's not something that I just wanted to be my whole life or anything. A lot of my life, I didn't really know what I wanted to do. I just kind of assumed that I would, I was interested in science. I'll go to college and, maybe graduate school if I'm still interested. And, at the end of college, we're roughly at the time when I was, I think, doing my internship, I had decided that, I wasn't done with courses, that I wasn't done with learning from kind of this course setting, learning in, kind of a broader context, where you get this choice about what you're learning, which you do get a lot of choice in college and in graduate school. Even you get a fair bit of choice about what you're learning. Once you go into more into your career, you're clearly going to be learning a lot, but where you're learning it and the allocation of your time and energy to learning it is can be more fixed, right? It's not not necessarily under your control or easily under your control, and you also then don't necessarily get to easily share that with other people. And so it's the combination of not being done, and wanting to share and contribute that led me to go to graduate school. So then I went to graduate school, and when you go to graduate school, there are a few things. One is UTA, so you teach. So again, that's one avenue of sharing your knowledge. Then you also are, you get involved with research projects, right? And you get to see the fun, the excitement, the drudgery, everything else about the academic life, right? And you get to interact with. I was lucky to interact with people who were working in industry. And we're at industry research labs, and so you get to see those. You get to have some of that experience, get some of that knowledge from those people, kind of vicariously, but you then have your own set of things that you get to explore and think about. So that's. That was enticing, those two aspects, having both the teaching and then being able to have my own ideas, my plan for research. So that that became, that's kind of a unique, it's a unique role that a faculty has. So that's then, that was at that point, it's, let's try this out.
I think one of the best quotes I've heard for like general life advice is, it's splitting your time up in 3 different ways for 3 different groups of people. 33% of your time, granted, this is probably more, you're going to allocate more for you personally as you're a professor. 33% of your time goes to people younger than you so you can pass on wisdom and knowledge. 33% is spent having fun and learning with peers. 33% collecting wisdom from people older than you and smarter than you. I think that's a really nice way to go about, trying to figure out how I should, while taking knowledge, you should also be giving knowledge to people who are still learning in certain fields. Like, for instance, I play guitar, I try and help out my friends, be like, oh, I'll teach you how to clean your guitars or maintain them and stuff like that. Or it's like, I come on the podcast and I'm like trying to share, like what with whoever wants to watch the podcast. Or I see, it's like, that's like how I'm trying to get back, like with this podcast and stuff. Because originally I'm like, I think it'd be cool to like talk to bands and stuff. So originally I had bands and stuff on here, but now I'm like, now that I know Iowa State has like this awesome podcast room, I'm like, I want to get some professors on that. I've actually had a great impact on my college career. It's like 381, probably one of the hardest classes I've ever taken. But it's also one of the most rewarding classes to get through because you're like, you get through it, you're like, it's over. I can't believe I did it. It's one of the most gratifying classes to take. Though you get in there, you're like, I don't know what I signed up for. It's like for the first lab, it's to go through the entirety of digital logic again, kind of make your own register file, and then I can't remember lab 2. I think I only did
That's lab 2.
That's lab 2. What was lab 1?
You just get used to the tools. You learn a little bit about VHDL. And the ability to debug. You see at least 3 errors, the 3 common errors that you would see. You see it in the first lab, and then you create a multiplexer to choose between input signals, and you create an adder subtractor. So that's the first 2 weeks.
Yes, it was.
So,
okay.
So yeah, the first 4 weeks are digital logic in VHDL.
Yeah, like the thing that tripped me up is like, so the starting 381 is like, that's what we weren't learning about in lectures, so I had to go back to like the 281 lectures and slides, which are easily accessible, so that was nice. And then you have the diagrams and stuff that Dr. Stoichev has out there, so that was a nice feature. But it's like, 381 is a big course load, and at the time, I don't know if you're familiar with ComS 309, but that's like another very big project course. And then I was taking CprE 310, which is like discrete math, then ethical hacking, and then intro to database management. And I was working like a part-time job. So I was just like, I really did myself in that semester. But it was, at the same time, I had a lot of friends that helped me out in some classes, like, having friends that you can, go to just for like ease of access for clarifying on something rather than having to wait for office hours, or if you can't make office hours or the TA office hours or something, you're just having someone you just explain it a different way. Because if there's anyone that I can see in like my peer group right now that would be a great professor, it's probably him. He's very good at reiterating information in a new way. So it's like finding friends like that, I feel, is very important for like your college career.
It probably is. You had asked me a question before about, is there a project that pushed you to your breaking point? I don't know that there is ever really a project. And I think so often it comes from what you just said, right? At least from my experience of, there are 5 courses you're taking. Where sometimes if you're, potentially are making a bad decision, 6, and so you have just a lot of courses, and they stack and they interact in not non-ideal ways, right? And that can put pressure on different courses. So I remember I had a algorithms course, and at some point I just realized, like, I'm not spending any time on my algorithms course. It's number 6 in the queue, in my priority.
No pun intended.
Queue. All right, and I'm just I'm not getting anything out of it. So A, I'm going to not do well. B, I'm not getting anything out of it, and B, it's going to mean that if I try to get anything out of it, I'm going to do poorly on everything else. So I dropped that course. That was one of the best decisions I made. Just dropping a course. I wished I had done it a month earlier in the semester. So, because then refocus my whatever 3 hours a week or whatever I'm putting into being in lecture. You know, I was still attending, but it just wasn't getting the attention that it deserved. And I remember some things from it, but not as much as I probably would have had I originally just spent more time on it or taken fewer courses. And it ended up taking actually a more theoretical course for it, and learned a lot more. It was a different semester. Had more time, learned a lot more about the theoretical underpinnings of computing, and things that I've learned, used, to better understand problems and be able to better talk with people. Throughout my the first part of my career, so it's been it was a good thing. But that was one time when something kind of pushed me to breaking point, or to the point of action,
where you're like, something needs to change here, and actually taking that step to make sure that you don't just drown in the water. But no, like I was talking to Dr. Jones about this, so I had him on the podcast as well, and what I was saying to him, like, I think it's very important during your college career, before you actually jump out into the field in the real world, or any time in your life, you have to figure out, where's my breaking point. And just, I don't know, I like being like very productive and very like efficient with what I'm doing and stuff. So it's like, I feel last spring semester when I was taking 381 with you, and just all the ridiculous classes I was taking, I feel like that, I guess I can say thank you for inspiring me, because like now I'm in talks like trying to do maybe like 2 other podcasts. My friends are like, so then I'd be running 3 podcasts. And I want to do the app idea I was telling you about. Then I think another fun project would be doing like real estate drone photography. So it's like, once I get my couple paychecks after I graduate here from Iowa State, I want to allocate some of that money to buying, just like an entry-level drone, but then doing the FAA test, then Part 107 test, and then, actually talking to, I know a couple of real estate agents. I'm like, hey, if you have any luxury properties that you want to get more aerial photos on, let's make something happen, because you can get like a couple $100 from that. So like, it's a weekend project. So it's just like finding ways where it's like you can still have a hobby, but it's still something productive, and it's like, gratifying. It's like, hey, I'm helping this person sell his house, or I don't know, I think brewing something like mead or kombucha, or just something where it's like more hands off, where you just kind of like let it sit and do its thing, and you come back, you're like, oh, now I can do this again. I don't know, just like I try and like come up with ways where it's like, just having something fun, but it also like helps you out.
Yeah. Although your hobbies can become like a job if you're not careful. So
yeah, this is true. Yeah,
I've occasionally had a hobby or two that becomes a little bit more like a job. So
like, what are you? Do you care to dive into that a little, or no?
Oh, sure. So beer brewing.
What got you into that?
What did I enjoyed beer, and in college, like to drink it, and something about that curiosity thing, right? I want to know how my computer works. I want to know how beer is made, right? So if you look at beer, it kind of looks like a magical thing that gets produced, right? Like manufactured, right? Like, at least that was me, in college, right? You get it in a can, you pour it out, it's clear, and has carbonation, and all of these things are like, well, how did that happen? Like, how did it get in there? And how do you make it? I have some understanding. My parents had a vegetable garden, like actually a plot of land outside of town, and that we went to many times, 3 times a week or more, and so I understood where like food came from, or at least some aspects of food, but like beer is like different. So the curiosity probably is what really got me into it, and then you get all of they're fun gadgets and things that you can geek out about. Again, kind of the engineering building end of things was got hooks into me too. But yeah, because a lot of work. And
So what about that made it a full-time job for you? Like, what were you doing with it?
well, it didn't make it a full-time job. I mean, so it didn't make it a full-time job, but you have to you have to transfer things on a certain date. You want to make sure that some of it you're consuming in a certain amount of time, and that means you have to have friends. You have to have a social life or something to get rid of it, right? Like, or you're dumping it, which is stressful too. So. You have to do things at certain stages, and that management of that is just annoying.
You didn't want to try and like sell it or anything?
Oh God, no.
Well, one, you have to get your manufacturing license for that, but to actually sell it in stores.
Yeah, and I having to worry about somebody else's taste. That's
You're
a lot of
worried
stress.
about the critiquing and feedback.
No, I'm worried about having the amount of, if you want to actually make money at it, right? You have to sell it to somebody. Somebody has to want it.
Yeah, this is true. Yeah,
And that it was a hobby.
yeah,
It was a hobby, clearly a hobby.
yeah.
Not not anything I would ever want to go into myself.
Right. So you're just doing it just for yourself, just see how it worked.
Yeah. But it felt at some points it was like, wow, I have to get up and I have to do something, because of this before I shower or you have to actually have to do it at a certain point, and it's So anyway, that's
Well, it's like with gardening though.
Gardening is exactly that.
Yeah. Well, it's like gardening to me is like does it actually save money, like doing your own like little homegrown garden? Because like I feel like the stuff that goes into it can be not as cheap as what just because the people do it commercially, and that's how it gets to the stores, as compared to just like your little small like what your parents did.
It's a hobby.
Yeah. But I feel like the quality of food you get from your own stuff, if you do it good, it can be better than what you get in the stores.
Depends. Depends on what it is and what year it is for you. And some years are good, some years are bad. But it's a hobby, right? I mean,
yeah. I don't know. Tomatoes, though.
I view it. From my observation and my experience. That doesn't mean it's not a satisfying hobby, right?
Right, right. Hobbies are supposed to be satisfying,
right?
Yeah.
I mean, it can be, it brings people. You can do it with people. You can bring people together. It can, you get to spend time outside. You get some physical activity in. You all these things that can be positives, right? And by saying it's a hobby doesn't shouldn't diminish diminish it.
Right,
but,
right.
But on the other hand, right, it's not. I don't think you're saving substantial amounts of money if you start counting your time and.
Right. Yeah, because time is money too. Yeah, time
right.
is very, very well money. So it's like, is there anything of your hobbies where you want to turn it into a full-time job, or you're just satisfied? Well, I guess I should think you're also a professor doing your research, and then you're also like I had to wait like 2-3 months to even get you on the podcast. So it's like,
so yeah, no, I
probably don't even have time for really much anything.
I wouldn't want to turn any of my hobbies into work.
Right. I guess that also defeat the purpose of the hobby as well.
I like my job.
Yeah.
So I like my job, and I find value there, but that's where my focus is for the bulk of my time. So
are you able to talk about any of your ongoing research?
Sure. So I've done I guess broadly I have designed low power programmable systems in a variety of and looked at a variety of facets of those. So, basically looked at ways to do error correction for highly voltage scaled SRAMs. So the closest thing to your processor in terms of storing data. So how can we save power and energy in that system? Looked at how do I build in an automated fashion custom processors given a program. So targeting basically embedded systems. These days I've look at a couple of things. One thing that I look at is designing basically sensor nodes that are intelligent sensor nodes that can survive for decades with little or no maintenance. Okay, so they basically are powered solely by ambient energy harvesting. So radio frequency, solar, thermoelectric, vibrational, whatever happens to be in the convenient to the application. Basically have no battery. So there is batteryless computing. And what you can appreciate is that if you're trying to harvest from most of these sources, the energy that you get, the rate of the energy is highly variable, and in many cases, very, very small. Right? So like RF, it's orders of magnitude less than you would need if you want to power a Raspberry Pi, right? And actually, many orders of magnitude less. And so even for very low power microcontroller processors and processing units, you have kind of this imbalance. They may not be able to self-sustain. And so there's management of banking energy onto a capacitor to briefly turn on and do something and then die, right? And so do something, take a sensor reading, do a little bit of computation, maybe some filtering, or maybe some very lightweight machine learning, encryption, send some data over a radio. And then you die again. And then you're off while you're banking some more energy. So I design these systems. I design how to do more efficient computation on them, how to manage time when you don't have any notion of time when you're unpowered, how to communicate between these nodes, because you mostly need to be on at the same time to communicate.
When you say design, are you saying you're actually prototyping these, or are you just saying how it'd work out on like paper?
Both. So we're partway through. So hopefully this summer we're putting out our test bed. So we have in our lab we have a test bed that will have a handful or a couple handfuls of nodes that are highly configurable, so we can run a variety of experiments, both computational experiments, kind of application experiments, as well as experimenting with communication and so forth. So yeah, we are really prototyping them. But when you want to evaluate an idea, you want to evaluate it quickly, so it should make sense at all levels. So it should make sense at the first order analytic model level, right? So I should be able to use some, kind of whiteboard and, equation based, okay, hey, is this going to work out roughly correctly? Does it make sense at all, right? So, I'm not violating physics to the best of my knowledge, right? So if it passes that check and you have a big enough benefit, then you might model it in more and more detail. So we might, we have a fairly accurate simulator that we've built that we can also simulate it at in, a very fine-grained, at kind of microsecond level detail for how this system is going to behave, and we've calibrated it with real measurements, and we have then our prototypes. So
That sounds like there's a lot going into it. So I guess how many people are working on this project with you?
well, I guess it's probably about 4 faculty in total, including myself.
Here at Iowa State, or
Yeah.
okay?
Yeah, here in our department, in ECPE, and then 4 or 5 grad students at this point. So that's 5 PhD students, and we have lots of undergraduate students, and we've had several master's students who have worked on it over the past now almost 4 years. So
Oh wow.
3 years or so.
Yeah.
So that's prototyping takes effort, and it takes a diverse skill set.
Oh yeah.
So commonly in computer architecture, things aren't prototyped. So at least over the last 20 to 30 years in computer architecture, for example, the most common way to evaluate an idea has been what are called cycle-accurate simulators. So basically, these are usually C++ models of processors that you can configure very easily and very flexibly, and they model what is going on at the functional unit level in the digital design. So adders, queues, caches, that sort of thing, right? So the hardware data structures, it models those at that level, and at the cycle level. So every period of the clock cycle, and so it's relatively easy to change and to implement things, although harder than first order models, as I was talking about before, where you're kind of reasoning about it with a say a probability distribution and or a queuing theory model or something like that. But that's the common approach that people have used, including myself before. And then occasionally they'll prototype something using a synthesis flow for an ASIC flow. Occasionally I've done that, or thrown it on an FPGA. That's rare. Those are rarer than the cycle accurate one, because they're more effort, and in many cases, right, you want to get out your idea, your insight. You don't need that level of detail that you would get from a completely functioning prototype to design. But yet, almost no one fabricates chips. There are people who are in more VLSI, etc., who'd fabricate chips for their research, but it's uncommon in architecture, certainly outside of industry, very uncommon. Industry has does test chips and such more commonly.
Do they send you test chips to work with?
Not me, no.
Or I didn't know, like, if you guys were working on like a department or organization, like you, the faculty, the undergrad, the grad students. I didn't know if you guys were like collectively a single group where maybe Intel or AMD or whoever the other chip manufacturers out there would be like, oh, we like the project you're doing. Or I didn't know if you could like talk to them and be like, hey, can we get some test chips or later down the road when you actually do break out of the, just simulation.
Yeah, so that's not common. That doesn't mean it doesn't happen to people who are very close with industry. There were some rumors of some test chips that another group was doing that I'm aware of, but years later I don't see the I have not heard anything of them. I've seen any publications with them. So it's certainly not very common. It's in terms of cross pollination from academia to industry. It's very you can see it's fairly common for those ideas to flow in that direction, right? And in some way, shape, or form. It doesn't mean every idea, but there's a reason that we do research. There's a reason, in part that industry funds research through a variety of means. But the groups who do that generally don't have anything to do with the actual physical design, right? So they're at the cycle accurate model. They have their own detailed models that are their model, not the industry model. So that's I guess where it is in terms of. But so to me it was a big change to actually start prototyping things. So I have yet to prototype a chip, but we prototype the whole system because the energy harvesting front end has such a tight coupling with the actual computation of what you can get done or not done when, and how much energy do you spend doing it when, that matters. And so the having the prototype and going through the process of prototyping was essential to A, being able to even build a simulator, but B, to really understanding the problem and proving that it works. Because it's easy to say, it's never going to work. In fact, many people have said it's not going to work. And in fact, it can and does work. But it takes effort.
So I guess with research projects, how much paperwork is really involved with that? So I guess as someone who doesn't do research, what do I research? I'm an undergrad. I'm going into a defense contracting work through BAE, but I have no idea really how research work really goes, like the paperwork involved with it. Because I was talking to Dr. Jones, and what he was saying was the National Science Association will loan out money to certain projects and stuff upon approval. So it's really selling the idea to actually get the project underway.
Yeah, so NSF, or National Science Foundation.
Sorry.
It's not so much a loan. They are, paying, an award.
Like a grant.
A grant to you for the purpose of having you do the work to, basically evaluate your idea, right? And to explore whether that area is useful or not, develop it further, and basically have impact, right? To publish the results of what you do, and there are other added benefits, right, that they get. I mean, they're supporting the education of graduate students, right, of the workforce. And so there are certainly opportunities, not just graduate students, undergraduate students that I support from NSF, who are involved in these projects, and they're getting training and benefit from it. And some of what I do also goes back into the classroom, right? And so it has also helps those students as well. So any student who I'm teaching, or it's also benefiting in that regard. So some of the one of the grants that I have, also has a kind of larger, more education component as well. So for that, I'm looking at trying to actually get students to prototype and fabricate working digital designs, okay, in an application-specific integrated circuit. We actually, I'm starting out with senior design teams, and we've one chip that's supposed to start fabrication soon. We've submitted it. It's been submitted for a long time, but it's a long process, and the flow is experimental. So, but in any case, that's supported in part by by this grant. And basically, I'm trying to get this experience to be across seniors, juniors, and sophomores. Kind of with the thought that if I can get you to be interested in 288 with being able to bring up a chip, so learn about the process of debugging when you have a digital design, right? I mean, it's fixed at this point, right? You get it back. Bring up is when you get the chip back and you start powering it, and you hope that it doesn't start smoking, but you hope that you can actually start to use the design. So you have to verify that your IOs are working, get your clock up and running, all of these things that basically we take for granted in almost all of our courses. But they're very practical things that you need to worry about if you want to actually make a device. So yeah, the idea is after 288, you're probably ready to actually work on this, whether students realize it or not, because it's doing a lot of that sort of embedded programming and sort of thing that you may have done with the Roomba. And it gets you skills and a story that you can tell in an interview. So if you're really interested in getting into a chip maker, this gives you things to talk about in perspective that they will appreciate. Things that I learned on my internship, you can learn through this process. So that's something that I'm excited about as well. But yeah, so that's so it funds both the research that I do as well as some of the other impacts that I have on our students, our workforce.
Yeah, that was really interesting. So I guess looking back at your internship with AMD, how big was AMD at that time? Because like now it's like when you look at AMD, I guess as someone who's not just doing like computer engineering or software engineering, a lot of like people in like PC building for gaming, they're like AMD, like the Ryzen series are actually a very applicable chip that is a little bit cheaper than the Intel comparison.
How big was that? I don't know the numbers. So I was there in 2009. Right after the financial kind of crisis was unfolding. So they'd actually laid off some people. They had just purchased ATI, so they purchased into the kind of the graphics market, and they were just spinning off Global Foundries. So it was a time of kind of, it was an interesting time, and I was it was that gave me the opportunity to see from the inside of the industry a lot of different forces, a lot of different perspectives. There was a lot of talk at the time about Intel and Intel's market practices and so forth, which AMD was in the process of, and may still be, suing them and in various countries. So AMD was obviously has been an important player, but was not the biggest, and still isn't, right, the biggest player in terms of
right
processors.
Yeah, I was just curious as like AMD. I feel like AMD has actually really grown over the years, like especially between like 2014 to 2020, just seeing really that growth of popularity in like even like pre-built computers.
Yeah, well, I mean, AMD's always had their followers, especially in the computer building and gaming community, right? The first computer I built was, I don't know, earlier mid 2000s, an AMD processor. So Yeah, I mean they've always had, I think, a niche there.
Yeah, absolutely. Well, then they came out with the Threadripper, and it was like that was the hottest topic at the time for like computer chips and stuff like that. Which I don't know. I feel like that's more for like cinematography and like rendering and like video editing and stuff like that. I feel like that's really what it was catered towards to. Because I was like, I think it was like almost like a $2,000 computer chip at the time when it came out. It's like, yeah, I have no idea. But are you still involved with like gaming or like doing your own like
I,
computer building at all?
I am. I've never really been involved in gaming. Yeah, I know I may have started with the discussion of the game, but I played some pretty, you know, more educational games.
Yeah.
I guess it's educational. Yeah, Amazon Trail, Oregon Trail type games. But I haven't really played games in. Well, I don't know that I ever seriously played games, but I actually have in my garage. I have a stack of video games that I haven't touched in 20 years that I'm trying to get rid of. So I just haven't been able to like find a spot for a home for them yet. So
Yeah.
and,
Throw it on eBay or Craigslist or you can find the I don't know if Ankeny or Des Moines has a disc replay, but it's like kind of like a retro arcade kind of video game store. It's always out there. I don't know, or you save them for your kids, or
I don't wish them upon my kids.
well, there you go. But I guess the next question I have for you: are there any personal projects you have that you're currently working on outside of your research? Just like something you do at your house or you're doing with a group of people, or any projects you've done on your own in the past.
Nothing that would be out, like no big collaborative project or anything. I have a couple of kids and spend a lot of time with them, do a lot of projects around the house, but those aren't probably that interesting.
Like electronical projects, or
Not so much. No. I spend a lot of my electronic, thinking is often related to either teaching or research, or relating it to one of those. So that's my outlet for my or electronics.
So then you go home, and then it's different realm of projects.
Yeah, well, I guess I built assembled. I wouldn't say built, but assembled one of these flight radar monitors, right? That takes the ID from the plane and translates that information and uploads it to the the database, and so my father-in-law can have the upgraded information, access to that information, because he loves plane watching. So, but that was not really.
No, it's still neat though. I mean,
in a lot of ways, I don't have a television. I kind of try to avoid
really
electronics when I am not using them for work and such, because you spend a lot of time on them for that purpose. And
so you don't let your kids watch TV or anything, or
well, I mean, kids watch TV a lot of places.
Yeah.
School and daycare being one of them. And you can watch TV on a smartphone. So occasionally they'll watch things. We watch aircraft documentaries with my in-laws, and airplane crash investigations mainly. Like it's maybe a little morbid, but whatever. My favorite ones are the ones that are like near misses,
Yeah.
or not near misses, or like there's actually a crash or whatever, but disaster for most people was avoided. But yeah, so it's not so much led as it's rather than being a central focus where I would sit down and turn on the television all the time. You have to watch it on your phone if you're going to watch it, which you can appreciate that it's not quite the same experience. So you actually have to kind of want to watch it.
I don't know. I feel like it's almost flipped for me. So it's like when I'm at home, this is like I don't have a personal TV here in Ames, but it's like when I go home, it's like I'm more just ease of access to get on my phone as compared to actually like sit down on the couch and like you get the remote and then turn on the TV and pull up whatever Netflix or whatever. It's like I don't know. I feel like I spend more time like watching like YouTube or whatever, like watching like I don't know. My thing is like the watching like the police body cam videos and stuff and like just watching the how they interact, like the good cops versus the bad cops, whatever, what they should do, what they shouldn't do. Just like I think it's very interesting just to see like those interactions and stuff that might not be widely public, what the news covers or something, just like stuff like that.
Yeah.
Just figure what they have to go through is like, bless their hearts, I couldn't do it. There's no way. I have a buddy who's a deputy down in by Newton, and I'm like, he tells me like, I think one time he had to do like a break and enter because like they had to do like a meth bust or whatever. He got to bring his own gun and everything. I'm like, you're living the life I don't want to live, but hey, someone's got to do it, man. Props to you.
Yeah, that's must be quite a challenging profession.
Yeah, but it's his ways. Like I like just serving the country and just making sure the world's a better place. I'm like, well, good for you, dude. I'll go just sit behind a computer and do some coding.
Yeah, everyone finds their own way to contribute, I think. Yeah.
Oh yeah, yeah. It's very interesting to see what kind of leads people down the path that they end up. That's why I like to ask all my guests, like, well, what led you on to be, researching a computer chip architecture? Well, my buddy, his dad was from, I think Israel, I think it was Israel, and then his dad fought in like two of the civil wars that Israel had, then migrated to the United States. So his dad has a combat patch from Israel. He's like, well, I gotta be like that. And so he's always like tried to live up to like his dad's name and stuff. So he went over to Saudi Arabia, did a tour over there, then came back. Now he's a deputy for the police department. So it's just like that's his way of giving back and defending. So it's like I always like ask him like, well, what made you want to do what you want to do? And this goes with anybody on or off the podcast. It's like I think it's very interesting to see what kind of like inspires people to take a lead onto something with their life. Yeah. But I guess next question. Let's talk about the Harpole accolade that you got.
Yeah, so I guess it's a assistant professorship. So I'm an assistant professor. I think we were talking probably before we started recording.
Yeah, probably.
Yeah, I've been here like 5 years. So I'm an assistant professor. Before it, I was directing my PhD program. So, I'm a quote unquote young professor, and there is an award, or I guess to say it's a professorship that is, for people who are faculty who are here within their first, I don't know, N years, certainly within their first 6 years, and basically it's kind of to support them in their kind of scholarship, their research potential, right, and to help kind of expand that, and so that's kind of the why you get it. Basically, it's funded by external donors. So this would be, I believe, the Murray Harpole, and so he was a former an alumni of Iowa State, and an entrepreneur, made money, was impactful in starting Pentair, so it's Harpole-Pentair professorship, and so the basically gave back, right? So you were talking before about how people choose to to then contribute back. So not only was did he start a business, it provides services, employment for a lot of people, but then also gave back to Iowa State, and this is a somewhat, I think, unique. In terms of being focused on a young faculty, a lot of these sorts of professorships are focused on more senior faculty. If you look at other institutions I've seen, and a lot of those are at more senior level. So this is in that sense kind of unique, and it's quite helpful in order to support me in having my own vision that can kind of expand beyond kind of one project, as well as supporting my graduate students in having a larger impact. So that was something that's been useful to me, and I had the opportunity to meet his daughter, and get a connection to people who were at Iowa State before. So it's nice to be able to have that connection, be located in a place that has history and where it's made a difference in people's lives to the point that they want to contribute back. So
yeah. So what does this award specifically do for you or anybody who's awarded it?
yeah, so basically, it gives you access to some money that you can spend, on a variety of things to boost your research, lab, basically. So, which is, we talked earlier about, a grant. So grants are meant to fund a specific project. And so you prepare a budget, and, this grad student is going to work on kind of these type of topics, and they're going to, produce X, and you have a certain amount of potentially, equipment that you may need, or supplies that you include because it's, unique to that project and wouldn't just normally be, available to you. So then, but it's all stuck in that budget. You have to have planned it out, and then you basically get that material as you need it for the project. This is allows me to explore things that may not have been in a proposal, right? So or buy a piece of equipment for something that I think would help me for the next proposal.
Okay, so it's more of just like hey, here's X amount of money, and use this to go towards your next step of research before you really have something set in stone, like a grant would be through NFS.
So
or NSF, sorry.
NSF or a contract through DARPA or right. So yes, although it's it's one of those freedom things, right? It gives you the freedom to choose how you think you can best build your overall research program, right? Your lab, your reputation for it. So could be for the next proposal, right? To bring more money here. Could be to take the next step on your idea from this project, right? To build that reputation, build your impact, make it potentially more easy for somebody to pick up on that idea, right? So I've been something that we haven't talked about. I have security work as well that I work on in terms of hardware security and automated approaches to improving hardware security. And so I've been working on that with this in part. So it's helped bolster that aspect of my program, my research program.
Do you like the security research more than the computer chip architecture research, or is it pretty much equal? Or do you favor one over the other?
I mean, the security work that I do is related to chip design.
Okay.
So it's not either or. It's both.
So is it the security? Because I know you're working with SRAM in the one,
right?
And this one you're working with security. Is it kind of like a sister project to the? Are they related?
So, SRAM is a fundamental building block of our current chips. Right. So building caches, scratch pad memories, tightly coupled memories, even FPGAs. Many of them are built on SRAM blocks. So SRAM is a technology. It's used in a lot of ways, right, in chips. And my previous project was focused on allowing them to operate at very low voltages where they incur errors. The project that I work on, and by the way, I've actually worked on part of my battery-less systems. I've touched on SRAMs, and there are people who have indeed used SRAMs for security purposes, physically unclonable functions and such.
I'm actually doing a project in 440 right now with those.
Oh, nice.
I think it's trustworthy IoT devices.
Nice. And then what I do with security right now, I am looking at the overall microarchitecture. Okay, microarchitecture being the implementation of a particular chip. Okay, so given a interface to software, then you actually have to implement that interface. The interface is the instruction set architecture, ISA. You actually have to implement it with things like SRAMs and adders and other registers that hold smaller amounts of data than your SRAM. So you put all these things together in some way to implement interface to software, but the way in which you put it together can make your computer more or less secure. And the goal is to, given an understanding of that relationship between security and how you've constructed your chip, which is non-obvious, I would argue. Since I've been at Iowa State, the global community, which has been, and this has been public in the news, has learned a lot about that non-obvious understanding through Spectre and Meltdown, basically speculative execution, transient execution attacks. So it's not obvious, but that can impact security. You also have tools in your tool bag, basically design patterns that you can plop in different places to improve that security. All of these things have a cost. Right? They may have a performance cost or an energy cost or an area cost, which is kind of, for chip design, the area cost is really the dollar cost in some sense. You can make a really big chip, but your yield will be really low if you make a really big chip. So it just costs more money per chip to make it, and more dead dies. So given those costs, right, you want to kind of design a chip that is secure and robust to a lot of different attacks, right? To kind of like all of your known attacks, you want to kind of have that some threshold of security against them, and then you want to have the highest performance, the most energy efficiency, whatever other metric your particular market demands. And so the question is, it's hard enough to do that manually. Can we make it a lot easier by automating it, right? So, targeting things like startups. So with the open sourcing of ISAs and CAD tools, or they're beginning to be more and more startup chip design companies, where it used to be going the other direction. And so if you are trying to design a chip with a small number of people, can you do this optimization in an automated fashion, get some understanding of your security vulnerability, et cetera. So that's what I'm looking at. And so I don't view that as being like, it's still about the chip design, right? You're still talking about that same design, right? The same components, many of the same analyses, but you are thinking about the security problem, right? So, in some sense, I collaborate with security faculty on it, right? So I bring some of the underlying hardware, more hardware design perspective, and I get to learn about more and more of the security implications, right? So I don't know if I like it more, but it's new, and back to that curiosity thing, right? I like to solve new problems. I like to think about new problems. Otherwise, things can stagnate. There are indeed some faculty who think about one problem for their entire career. That's not likely to be that's not my perspective. That's not what I want for my career. So, so this is an issue that is, important, and so I think it deserves solutions, deserves to be better understood, and so that's why I'm interested in it.
Yeah, no, I think that's awesome. I know there was another award that you got that you want to talk about. Did you want to talk about that?
I think we already did.
I
think we already. Yeah. So
was that the NSF?
that was one of my NSF awards, talking about the chip design. So we and the educational component.
I guess I didn't make the connection that was the National Science Foundation.
Yeah. So that was my career award. And so it was a batteryless intelligent computation, and then some aspect of it is chip design for students. So
that's so. I guess what can you go through the steps that actually really got you the reward for that?
The steps.
Like, I guess, how are you noticed by NSF?
Well, so you propose. So you write a proposal.
Okay.
So you ask, right? So it's not an award. It's not like somebody's like, oh, hey, you're cool, here's an award. You are asking for money, right? So
it's just the process of getting the grant for that kind of research.
Right.
Okay.
Right. So grants are called awards.
Okay.
So
I guess that was a misconception on my half.
Yeah. So I mean, I guess there are several different ways in which you can get funding, but kind of the a typical one for NSF would be that you identify an area that you believe is an area that has kind of an intellectual gap, and you believe it's an important area to fill out, right? To understand, right? It might have might have important safety impacts for people. It might have monetary impacts, economic impact, right? And something that is right that you're an expert in, probably, right? Or like that you're using your past expertise to look at and solve, right? And so you kind of narrow down that idea, into a proposal. It's like 15-page proposal, and there are many other components. There's a lot of more paperwork, but like the core narrative is 15 pages, 10 to 15 pages, and so you write why the idea is important and sketch out a plan for looking through that idea. This idea is going to produce, a bunch of papers, showing the work that you did, and so like smaller ideas, right? So, but when I say idea, I mean it's more of a vision. It's not just a course project idea. It's
Right.
Whole vision area that covers 3 to 5 years of time, right? That you're gonna work on it. And so you go through all of the planning, as we talked about before, budget planning. How many graduate students are you having? What fraction of your time are you going to be spending on it? What resources do you need? What resources do you have? How does it synergize with other things that you're doing? And so, indeed, the career award involves both synergies with your department and with an educational plan, a bit more significant than other awards, other NSF proposals. And so, but yeah, you submit it. In terms of NSF, then they evaluate it, and it goes through a panel of people roughly in your area, in your area. They evaluate. They read through it. They look at your some portion of your past work that you've. There's a limited amount that you can put in that other portion. So they look at some portion of it, see if you're kind of qualified to do it, and if your idea, is, in line with, things that need to be done. It could be impactful, it could be interesting, and so they evaluate its merit. Kind of they grade it into one of 4 bins, and then the NSF program officers can then decide of the ones that are kind of the sufficiently high bins, which ones will get funded, and then they get funded, and then you do the work.
No, yeah, because I was like trying to figure out, like, how do they go the approval for the proposals? So it's like I think that was very well understanding how you said breaking it down, how it goes to, because it makes sense. Like, you wouldn't want someone who doesn't know anything about computer chip architecture reviewing your proposal and be like, sure, we'll give this guy the money or whatever. It's like you want something that actually knows, something like you do to validate your proposal.
Right.
So yeah, no, that makes total sense. Thank you. So I guess speaking of students helping you with your projects, but putting more of a focus on the students, what tips do you have for students as we're wrapping up here with about 15 minutes left?
Okay. What tips do I have for students in general?
Students in general, people in general, anybody, everybody listening.
I like to get advice from other people too. So you're 30, 30, 30, or whatever. You're one third, comment. Although I had a lot of friends who are now pretty much elderly. So, because I hung out with people who had lots of life experience. I listened to them. So I think you'd mentioned earlier also that you've talked about with other people about ChatGPT, coming AI, and the potential for things like going on more online or hybrid that we experienced during COVID. So all of these things kind of coming together. I think that flexibility, adaptivity, and the ability to learn and learn new skills, new tasks, and to think and think critically and vet your information. Like those skills, like are going to be pretty important for our students going forward. Myself, myself included too, right? I mean, I'm just thinking about from my perspective of how am I going to adapt to these things? Because I think that we're going to have a lot of those sorts of changes in what I hope to be my working career, and certainly what I hope to be my students' working career. And you're not probably going to be doing one thing for 30 years. Right? You're going to have to, pretty rapidly adapt as things change. And so seeing that over the last 5 years, that would be my encouragement to students, is to learn how to learn. Sometimes it may not even matter as much, what specific path you're taking and what degree you're getting. Right? There are a lot of degrees that look pretty similar around our department and those areas. That degree name doesn't matter as much as your ability to understand things, make connections, and think, identify the assumptions that you're making, what does a decision depend on, how to reason about it, how to understand if, ChatGPT is actually giving you something useful and correct, and can you use it or not use it? That sort of thing those are tough questions. They're questions that may change over the next 5 years, and so that sort of relationship with technology, I think, is going to rapidly change too. So
what's your opinion on ChatGPT?
Opinion?
Yeah, general opinion.
That's that's hard. It's a very open-ended question. I've played around a bit with it over the last, semester plus, but I still don't really. I still don't tangibly appreciate what I think the role of it should or could be. That's one thing I'm probably gonna spend a little bit of time playing with more in my kind of free time, but in my self-learning time, right? When trying to understand what other people are doing in the world with technology, understanding how that impacts my area, and not only my area in terms of computer architecture, but in terms of education, teaching, and ways in which it can help, hurt, and how it may impact, the humans that are going to come into my classroom in 5 years, because they may be very different people than the humans who are here now versus 5 years in the past, 10 years in the past, and the modes in which they access information. So appreciating that changes as well, I think. So I don't know what I don't know that I don't have a hard opinion on ChatGPT.
I was just asking for your general thoughts and stuff. I think ChatGPT can be a very nice, not a replacement. I feel a lot of people are worried about AI replacing a lot of things, which I don't think is ever going to be the case, because at the end of the day, we can see that a lot of people do want, humans working on stuff, just so we can cover those kinds of jobs and everything. But it's once you take away all the jobs and AI is doing everything, it's that's creating a less personable experience with a lot of things. Like the components you're buying for your research or stuff like that. It's you want, actual humans or to make sure that, these products are actually tested and stuff, rather than AI just pumping them out. And I don't know, you know what I mean though?
Sort of, kind of. I mean, the chips that we make, how should I say this? I mean, there's already a lot of, depending on how you say what is machine learning or not, right? There are, for example, synthesis flows. Those synthesis flows are based on heuristic algorithms that have some stochastic input to them. And yes, in some sense, they're checked at the end, but there's been a concern. There's a security concern. There's been a long-standing security concern there, where you could put in hardware trojans. Your tool, these are large, complex tools, could insert malicious hardware, and it may be hard to detect. So, in some sense, I don't know how much of a I don't know how much of a unique problem that's posing. In terms of I want my chip to be made by a human. Well, you may not appreciate how much of it isn't made by a human now, like when you really, really think about it, and how much automation there is in the manufacture process, right? I mean, of that chip. So, yeah, I don't know, right? In terms of how this technology truly fits in, I think both healthy skepticism, right, and the as best as possible understanding of what the tool is. How is the tool made? How do you expect the tool to react? That'll always be important. Where did you get the data to train the tool? Those sorts of things, right? There'll be important questions.
Yeah.
And I think in some sense they have been important questions, and they should continue to be important questions. But
yeah, no, fair enough.
It'll provide ample space for research and for ideas and for discussion. I think it also does hopefully emphasize the importance of being able to understand science and technology, right? And how that's important for not just some people, but for a lot of people, to really have an appreciation of these sorts of tools. I remember when my father, initially, brought home a computer, and he had been an accountant, but he basically programmed in COBOL back in the day when he was a student, and you worked for the University of Wisconsin as a student, was a programmer, and ended up working there his whole life, or his whole working life. And so, I was saying, well, how smart a computer was, and in sense, his response to that was, well, it's really only as smart as its operator, and that understanding, I think, has been important, right? It's what are you providing to the computer, and what actions are you allowing and you are expecting to take based on its outputs, right? So understanding is certainly important.
Yeah.
Right. And understanding how what you're actioning on, I think, is important.
Yeah. I think AI will serve a nice purpose and to help learn about stuff at a surface level. Like for your research, I don't think AI is developed to the point where it can help you really that much with your research. But it's like, let's say I wanted to learn how to cook a really mean fettuccine alfredo or something like that. It could probably give me a really nice recipe, or at least point me to a website that had one with 5 stars with a couple thousand ratings. That's kind of like the point I see AI like ChatGPT currently pointing towards. So it's like learning about stuff on like a very surface level view.
I mean, what you just described has already been around for 20 years, right? I mean, in terms of Google search, right? I, I think that right now people have plenty of examples of where ChatGPT helps for a lot of different, could have help, right? Has potential in a lot of different tasks that are associated with whether it's writing or writing code or generating um, uh, um, uh, generating boilerplate, right? Code. People could, could use, and there are other AI tools that do things, like try to infer what a piece of program does and write you a comment, and you can edit it, but it's a lot faster for it to generate it first, right? And then if it's mostly right, then you can fix it, right? So there are certainly uses. There are uses. I mean, my students write lots of code, right? So it could certainly theoretically increase the productivity of students.
That's what I'm looking forward to.
A lot of design optimizations may be improved, and the productivity of mapping to optimizations for designing a process, right? Like there are many opportunities for machine learning. People have explored some of them. There are going to be continued opportunities. So yeah, there's many opportunities to be able to and leverage machine learning, AI, however you want to, whichever end you want to talk about.
Yeah. I'm definitely excited for it, but I guess we got 4 minutes left. Are there any closing statements you'd like to give for the podcast? Anything you want people to know you for?
I don't know that I have any closing statements.
No general life advice about anything?
I think I've talked plenty about my advice, but I guess I would encourage people to act with integrity, with respect to themselves and others. But I think that's when you said what would somebody want you to, what do you want to be known for? That I would start with that. Other things flow from that. So
fair enough. Well, we'll end it there then.
okay.